Hi there. So we'll move to the next question on momentum and impulse. So this time a block of mass m, big M, is connected by a string and attached to a ceiling. So the length of the string is small l. Now from this side, exactly in the horizontal direction, a bullet of mass small m traveling with a velocity v. So this bullet comes and embeds into this big M. Okay, so this is the trajectory of the bullet. So when this hits, so when this bullet hits the big M, this start to oscillate. Okay, you can imagine this start to oscillate. So the question is, how far will the block swing from its position of rest before begin to return. So you understood the problem, right? So this time a block of big M is connected to a string and the length of the string is L, and from this side you fire a bullet of mass small m and which is traveling with velocity small v. So this is our problem. So the question is what? When this bullet hits this big M, it starts to oscillate. So let's assume it comes to this position, okay, something like this. The question is what? How far will the block swing from its position of rest from here before begin to return? Okay, so simply they are asking, okay, what is this theta? Okay, if you know this angle theta, you can say, okay, how far will the block swing from? So okay, if you know the theta, that's fine, the rest you can simply calculate. Okay, maybe they are asking the amplitude of this oscillation, right, the A. So how do you do this? So let's apply the conservation of momentum. So what is conservation of momentum says? The total momentum of the system is conserved. So the initial momentum of the system, you have only velocity for this bullet, not for this big game. But after this bullet hits the big game, we said this bullet is actually embeds into the system. So the final state of the system would be like this. Okay, so this is our initial state. The final state would be the total mass become small m plus big M, and it starts to move, say, let's say with a velocity u. Okay, so how do you calculate this u? So let's say apply the conservation of momentum. So the total momentum, initially it was mass times velocity, plus here no velocity, so 0. The final momentum of the system is total mass small m plus big M traveling with velocity u. So from here I can calculate the initial velocity of this system, okay, after attached with this bullet, would be small mv over small m plus big M. Okay, so this is the velocity of the whole system now. Well, now the question is now, what would be, okay, how do you calculate this angle? How do you calculate this angle? What I'm going to do is I'm going to use the conservation of energy now from this point to here. Here you have only the kinetic energy of the system, but when the object reaches somewhere here, you have only potential energy. So we will take this line as our zero potential level. Okay, so this is our zero potential level. So we assume here the potential energy is zero. So from with respect to this line above, you have positive potential. So let's use conservation of energy. So how do you use conservation of energy? So remember this, right? This is our initial velocity of the system. So I'll write down here the u is equal to mv by big M plus small m. So I'm going to use conservation of energy. So the total energy here, you have only the kinetic energy, which is half small m plus big M, the total mass of the system, times u squared, which is equal to, here you have only potential energy, which is m g. What is h now? What is the height? What is this height? Actually, I can find this height in terms of this L. Okay, and let's say this angle is theta. So what I can do is, you see now, this total length is L, and this is L. So what I can do is, now I can divide this length. Okay, so towards this angle. So this angle I can calculate. This angle would become L cos theta. Okay, this length is L cos theta, but the total length is L. So therefore this small little portion will become L minus L cos theta. So I can write down the height as actually L minus L cos theta. So I can take L as a common factor. So I can write down 1 minus cos theta. Okay, so here what I did, the height is actually L minus L cos theta. So I can take L as a common factor. So you will get 1 minus cos theta. So from here you see I can cancel out these two. So you will obtain what? U squared by 2gl, right? Gl will come down. So this side you have 1 minus cos theta. Okay, so yeah, so from here I can calculate the cos theta. Cos theta will become 1 minus u squared by 2gl. Am I right? Yeah. Therefore, actually what is our u squared? U is, we know, okay, mv by m plus big M. So I can write down theta is actually cos inverse 1 minus 1 over 2gl times u squared is mv by small m plus big M square. Okay, so this is our this angle. So if you know this angle, okay, in case if you need, for example, the amplitude of this oscillation, okay, you can calculate the angle here. All the values are in all the variables are in letters. So if you need some numerical values, you can just substitute all the values, the given values. You can find the corresponding theta. Okay, so if you know the theta, you can simply say what is our amplitude of this oscillation. For example, you see this is our L and this is our theta. So if you divide away from this theta, we will get this portion as L sine theta. Okay, so even you can calculate the amplitude of this oscillation. A will become L sine theta. You know what is theta, you can substitute and you will find the answer. Okay, so we'll move to the next question. Okay, so what is next question? You have a nucleus, you have a stationary radioactive nucleus. Okay, stationary nucleus. So the mass of this, okay, so here the mass is actually mass of, it has m units. Okay, this is units, m units. So what's happening is actually this disintegrates, this nucleus disintegrates and forms an alpha particle plus the rest of the residual nucleus. So this is our residual nucleus. Okay, so this is our problem. You have a stationary nucleus and it has big M unit mass, and this integrates into alpha particle plus the residual nucleus. The question is, if the kinetic energy, so Ke mean, I used to write down Ke mean kinetic energy of the alpha particle, is E. Okay, the kinetic energy of the alpha particle is E. You need to find what is the kinetic energy of the residual nucleus. So this is our question. Okay, and let's assume for the alpha particle we know this. Okay, I hope you know this already. 4 unit mass for alpha particle, the mass of alpha particle. Okay, well, so how do you find if this kinetic energy is given? Okay, this kinetic energy is given. You need to find what is the kinetic energy of the residual nucleus. So to do this, first so this is our question. Okay, I'll put a question mark. So first let me explain one thing. You know, kinetic energy is given by half mv square. Okay, so what I'm going to do is I'm going to multiply top and bottom by m, and I'll write down mv square. So you see these two are exactly same. I just multiply top and bottom with the same variable, right? M and m. So now look at this. This is m squared. So I can write down this as half m squared v squared by m. So what is actually mv? mv is our momentum, right? So I can write down this as p squared by 2m. So the kinetic energy can be written as in terms of momentum, okay, p squared by 2m. So remember this, this relationship, okay, because this is important. I'm going to use this p squared by 2m. So what is the total momentum of the system? The initial momentum of our system is 0. The final momentum is, I'm going to write down in terms of kinetic energy. Why? Because this energy is given, okay. So okay, I'll write down here, okay. We said the energy, the kinetic energy can be written as p squared by 2m. So from here I can write down p is equal to square root of, okay, wait. For the alpha particle, what is m? We said the m is 4 units. Okay, so I can write down here 2 times 4 is 8. So I can write down this as 8e, square root of 8e. So the kinetic energy, the momentum of the alpha particle is square root of 8e plus what is the kinetic energy of this residual nucleus, which is, we said, E prime. So I'll use the same equation. So I can say E prime is equal to P prime squared over what is the mass of this residual nucleus. I can write down as m minus 2m. Okay, so this is 2 m minus 4, because p squared by 2m, the mass of this would be m minus 4, because here we said 4, right? The mass is 4 units, so it should be m minus 4. So that's what here I have written, m minus 4. So from here I can say the momentum p prime should be equal to what? Square root of 2 m minus 4, right? 2 m minus 4. Can you see this? Okay, maybe I should write down here. Okay, so p prime equal to square root of 2 times m minus 4 into e prime. So this is our momentum of the residual nucleus. So I'll write down here the momentum we found, square root of 2 m minus 4 times e prime. So the question is, well, how do you find the e prime? Okay, remember this should be minus sign, obviously, because if the momentum of this particle is, let's say the alpha particle is this way, the momentum of the residual nucleus should be in the opposite direction. Because the momentum is a vector quantity, so by intuition you can guess this. Okay, so I'll put this minus. So I can write down this as square root of 2 m minus 4 e prime should be equal to square root of 8e. So from here, if I square both sides, I'll get e prime is equal to 8e by 2 times m minus 4 into, m minus 4, sorry. Right, you see I can cancel out 2, 8, so I'll get 4e by m minus 4. So this is the kinetic energy of the residual nucleus in terms of, we found in terms of big M, the mass of this one, with the kinetic energy of the alpha particle. I hope you got this idea, right? Okay, so we'll move to the next question. Well, so this time you have a conveyor belt. You have a belt right, what is conveyor belt? And here you have a kind of system which this delivers, for example, sugar. So this is our empty conveyor belt. I hope you can read my handwriting. So this belt is moving. Okay, so this is our belt. So the belt is this. Okay, so this is our belt. So this belt is moving with a velocity. So let's say it's 20 meter per minute. Okay, so this is moving with 20 meter per minute. And this sugar container, so this is our sugar container. So this delivers, okay, this delivers sugar at a rate of, let's say, at a uniform rate. Okay, so this delivers at uniform rate 30 kilogram per second. Okay, onto this belt. Okay, so the question is, okay, first let me write down an assumption. Assume the initial kinetic energy of the sugar on top of the belt is negligible. Okay, so this is negligible. Okay, so meaning when you drop the sugar, the sugar actually it starts from rest. Okay, so that is the idea. Because there is no initial kinetic energy, we say that is negligible. The question is, find the force required to maintain constant velocity. Okay, find the force required to maintain the constant velocity of the belt. So you have to make sure your belt is, even after you drop this sugar at this rate, you maintain the constant velocity of this belt. So how do you find it? So this is 20. Okay, so the first, let me convert this into meter per second, because that is our SI unit. Okay, so how do you convert this minute into meter per second? So 20 I can divide by 60, ms minus 1, so meaning 1 by 3. Okay, 103 meter per second. This is the speed of the belt in our SI unit. So we know Ft equal to mv minus mu, change in momentum. We studied this. So I can write down the force is actually mv minus mu by t. Okay, remember we said the momentum, the initial momentum, we set the initial speed or the kinetic energy is 0, okay, of the sugar. So I can say, okay, this part should be 0. So we have only mv, but when you drop this, the velocity of the sugar should reach this speed. Okay, that is the idea. At the same time, yeah, you have to make sure it maintains the constant. Okay, the question is what? You need to find the force required to maintain this constant speed. So what is the rate? The uniform rate is actually 30 times, and the velocity of the sugar, okay, it should reach this speed 1/3. So this whole thing, okay, this part becomes 0 because we said the initial speed is 0. So from here, if you find it, you will find 10 Newton. Okay, if you simplify, you will find 10 Newton. So this says in every second you have to give 10 Newton force to keep the belt, to maintain the belt at constant speed. Okay, so this is the idea. And the second part of the question, okay, for the first part, remember, we got 10 Newton. Okay, the second part of the problem is power required to maintain constant speed. Okay, what is the power required to maintain this constant speed? How do you write down power? Power is what? Work done by time taken. Work done can be written as what? Force into distance over time taken. Okay, what is d by t? Distance over time is velocity, right? So I can write down power means simply force into velocity, right? So I'm going to apply this formula. So the power required to maintain at constant speed, the force we found 10 multiplied by the velocity is what? 1/3, right? So the answer is 10/3 joule second.